This brief tutorial will explain how a multi-channel analyzer, or MCA, integrated into Quaesta's neutron pulse monitor device can make setting up your proportional neutron detector fast and easy. A multi-channel analyzer also provides valuable feedback for long-term health monitoring of your neutron detector. Quaesta's programmable NPM2000 neutron pulse module is a small package that contains a high-voltage supply, charge-sensitive amplifier, pulse shaper and amplifier, and waveform capture electronics. The NPM2000 allows the user to digitally set upper and lower pulse discriminator levels and has a built-in counter. An optional onboard multi-channel analyzer and data logger add functionality to this powerful and affordable device. A proportional neutron detector consists of a proportional detector, a tube filled with either helium-3 or boron trifluoride gas, or a tube lined with boron-10. An electronics device called a neutron pulse monitor or module is attached to the proportional tube. Generally, gas-filled or boron-lined proportional neutron detector devices exhibit a characteristic signal pulse height spectrum. The neutron pulse height spectrum is a histogram that plots the pulse signal strength or height of each neutron detection event along the abscissa or horizontal axis. Pulse height is often digitized into bins, typically 128, 256, 1054 or more bins. The number of counts within each pulse height bin is plotted along the ordinate. Moreover, the signal pulse height spectrum plots the relative number of detection events that occurred at each pulse height. The shape of the pulse height spectrum is influenced by both the underlying nuclear physics of the neutron interaction and the physical characteristics of the detector, including the type of detection material, helium-3, boron trifluoride, or boron, gas pressure, detector geometry, cylindrical, spherical, etc., and voltage. For example, the position and relative height of the main signal peak is dependent upon the energy of the products of the nuclear reaction, while other features, such as the shelf region, are more dependent on the geometry, the size and shape of the detector. To understand the shape of typical pulse height spectra, it might be easiest to consider the nuclear reactions in the detector and the detector characteristics, such as geometry, separately. For this discussion, we consider helium-3 gas as the detection material. Helium-3 reacts with a thermal neutron to produce a triton, a tritium nucleus, and a proton. The total energy released by this nuclear reaction is fixed. Because the thermal neutrons detected have negligible kinetic energy compared to the energy yielded in this nuclear reaction, the net momentum of the triton and proton is assumed to be zero. Therefore, these reactants are counter-propagating, and each reactant has an energy that is consistent with overall energy and momentum conservation. As these energetic particles travel through the detector, they deposit energy into the detection material, often a gas, and ionize electrons that are accelerated toward the detector anode and measured as signal. If the detector's active region is large compared to the mean free path of the reactants, all of their energy will be captured and measured by the detector. Since the energy of the reaction is constant, this will produce a narrow signal peak in the pulse height spectrum. The location and relative height of this peak is characteristic of the energy of the reaction. In most practical detectors in general, the reaction products are not fully absorbed in the gas before striking the detector wall. This so-called wall effect causes less energy per nuclear reaction to be deposited into the gas on average, and modifies the pulse height spectrum to create shelf features and a broadening of the signal peaks. To understand the origin of the wall effect, consider a reaction in which the triton is produced very near the detector wall. In this case, the energy of the triton will be lost to the wall, while the proton's energy will be absorbed by the gas and detected. If this same reaction happens farther from the wall than the mean free path of the triton in the gas, then the energy of both reactants will be absorbed and detected. Therefore, the deposited energy from these extreme cases will range from 0.573 megaelectronvolts to 0.573 megaelectronvolts plus 0.191 megaelectronvolts. And since all locations are equally likely, the energy spectrum will be uniformly distributed along this interval. This creates a shelf in the pulse height spectrum that spans this deposited energy range. Due to symmetry considerations under particle inversion, a second shelf exists that ranges from 0.191 megaelectronvolts to 0.191 megaelectronvolts plus 0.573 megaelectronvolts. The sum of these two independent features gives rise to the so-called wall effect in the pulse height spectrum. The particulars of this feature are strongly dependent upon the exact geometry, the size and shape of the detector. The pulse height spectrum of a real neutron detector may exhibit both a peak and wall effect shelf. Additionally, gamma rays and electronic noise introduce signal at the low end of the pulse height spectrum. This signal should be discriminated against and rejected when counting neutrons. Actual spectra are shown for helium-3 and boron trifluoride. Boron trifluoride has two peaks in the pulse height spectrum. Because the nuclear decay mode has two possible channels, this leads to two sets of nuclear reactants with different energies, generating two distinct peaks in the spectrum. In an ideal detector, the upper and lower discriminator levels should be set to bound the signal peak. In this case, all neutrons that are detected will be counted. For a real pulse height spectrum, the lower discriminator should be set in the signal spectrum valley to maximize neutron counts and reject gamma rays and noise. The total number of counts is equal to the area under the histogram between the two discriminator settings. Setting up a neutron detector, including the voltage, gain, and discriminator settings without a multi-channel analyzer, is a process. Since the underlying pulse height spectrum is not visible, it must be inferred from the way in which the neutron counts per unit time change with the discriminator setting. If the neutron count rate is low, this may become a time-consuming process. In the figure, as the lower discriminator setting is moved to the left, the counts per unit time generally increases, except for the valley region in which it remains constant. In practice, users often fix the lower discriminator level and increase the tube voltage. Increasing the tube voltage sweeps the underlying pulse height spectrum to the right across the lower discriminator. As the spectrum sweeps across the discriminator level, the number of counts per unit time changes, and the underlying spectrum may be inferred from these changes in counting rates. The inset graph plots the counting rate versus the tube voltage as the pulse height spectrum moves to the right. When the discriminator setting is in the region of the peak, the counting rate increases rapidly with tube voltage. This is indicated by the red line on the graph with a steep slope. As the shelf region moves across the discriminator, the counting rate still increases, but more slowly, as indicated by the blue line with shallower slope. In the lower shelf region, the slope in the graph is even smaller. Finally, when the valley region crosses the discriminator, there is no change in counting rate with increasing voltage, and the slope is flat for this region. Consequently, this region is traditionally called a counting plateau. If the spectrum is moved farther to the right, then the counting rate increases again, but the increase is caused by gamma ray events and low-level electronic noise. In general, the tube voltage versus counting rate graph is produced in order to infer the underlying pulse height spectrum so that the voltage and discriminator levels may be set to optimize neutron counts. Generating this graph may be laborious, especially in situations with low neutron flux or with complex structure in the pulse height spectrum. These graphs do not always have clear features that allow one to clearly locate spectrum features, such as peaks and valleys. Clearly, using the actual pulse height spectrum is a more direct and superior tool in setting your neutron detector parameters. With a multi-channel analyzer, the entire spectrum is visible, and it becomes much easier to set the high voltage and amplifier gain to make full use of the dynamic range of the device. Also, the user can see exactly where to set the discriminator values to maximize signal and rejection of noise and gamma rays. When using a multi-channel analyzer, the pulse height spectrum histogram fills in over time. It is then easy to identify key features such as peaks and valleys. However, even before the histogram is completely filled in, the user may readily identify sharp features and select the location on the spectrum for setting discriminator levels. In summary, the benefits of using a multi-channel analyzer with your neutron detector include ease of setup, clarity in setting detector parameters including voltage, gain, and discriminator levels, and the pulse height spectrum provides useful information for long-term health monitoring of your neutron detector. Changes in the shape or location of the pulse height spectrum can be indicative of problems with the system. Quaesta's NPM2000 neutron pulse module comes with an integrated counter and optional multi-channel analyzer. With RS-232, USB, or Ethernet interfaces, the programmable NPM2000 connects directly to your laptop, desktop, or netbook.